All right, welcome everybody. We are live. Welcome to our weekly Intro Physics 2 live stream. If you've never stumbled upon this channel before, my name is John. I have taught physics for longer than I care to admit, and I started in Berkeley a long time ago. I was a teaching assistant, or GSI, for Physics 8A and 8B. For those who know what that is, those are the two intro physics courses typically for pre-med students, but in general for life science majors, although some other majors do take these classes. And I enjoyed it enough that I ended up doing it for a long time. I've tutored it and taught it pretty much ever since, along with a whole bunch of other physics and math classes, mostly lower div. And over time, I got talked into live streaming, mostly by students who just figured that it would be helpful for them to get a quick recap every week of the important concepts of the week, and kind of break down a few simple problems they might be classic problems, but they're simple enough that we can talk about how you set up problems, how you go about thinking about them and approaching them, and then from there, hopefully it helps you do other problems in discussion or on your own when you're studying. So that's kind of how this came about. Intro Physics 2, or basically Physics 8B, is a class that's focused on electric fields all the way through a little bit of quantum. So this live stream is basically inspired by Physics 8B. It's pretty much the same material, roughly in the same order, and it'll go through electric fields, magnetic fields, induction. We'll do a little bit of optics at some point with some EM waves, just a tad of EM waves. And then it gets into interference, diffraction, nuclear physics, and quantum, pretty much. So it's kind of a brief run through of the curriculum, but that is what I mean when I say Intro Physics 2. And again, the goal is to kind of, after the fact, after you've gone to lecture, perhaps the first discussion, and you've been submerged with all this information because the class does move very fast, kind of regroup and say, okay, this is really what matters in each chapter. This is why this chapter is, the first chapter of the class and not the second one, and how it articulates with the second one. Let's do a few problems, and then from there, hopefully, it gives you a little bit of clarity as to, how to continue practicing physics from week to week. Now, I started a little late. We're about 2 weeks into the semester at this point, and I started late on purpose, actually, because students usually the first week are busy doing other stuff, and then from what I've heard, they prefer to have these recaps after they've kind of been exposed to the material, at least in lecture. So this week I'm starting. I'm going to catch up this week. I'm going to do 2 live streams. I'm going to do electric fields today, and then on Friday I'll do Gauss's law. And then at that point we'll be caught up. Next week we can dive into electric potential, and you might be a little bit ahead, I might be a little bit ahead. The beauty of a live stream is that you don't have to watch it live. You can watch the recording, and you can watch it whenever you want. Speaking of watching it and having access to resources, let's just go through this real quick. If you want to find this live stream, all of them, every week I'll put one out. You want them all in one container that's easy to navigate, that has also the practice problems that we'll do so that you can attempt them before you see them on the live stream, as well as some solved homework problems. You can go to slackademia.com/live streams. You'll want to enroll in the free course called Physics 8B Live Stream. And in there, you'll find all of these live streams organized by week and topic. And then within them, you have the text of the practice problems I'm going to do. Like that, you can follow along, or you can attempt them first and then watch the video. And then you also have solved homework problems. So it's kind of nice baseline. It's free, and you can go there and practice and kind of, explore all the content, and hopefully it kind of, gives you a bit more practice than you would get otherwise. If you really want more practice, you can sign up for one of our study guides. If you don't see a study guide for your particular course because we haven't created it yet, you can contact us. You'll send us your syllabus, and we will create we will create it for free, the study guide, but we won't sell it for free. So you'll subscribe, but The putting it together doesn't cost anything. So if you give us your syllabus, we will create a customized study guide, which will have lecture notes and videos, practice problems with video solutions, and practice exams with video solutions, catered to your syllabus. Then at that point, you'll see it on the website. You can decide if you want to sign up or not. It's $40 per month, and you can cancel anytime. But it is then a customized study guide for the class that you're taking. And if you want more than just a study guide, if you want me to help you with physics throughout the semester, then you can sign up for the Masterclass. It's the same thing. When you sign up, you can either choose just the study guide or the Masterclass. The Masterclass does cost more, but it comes with a guarantee that if you don't get some kind of A minus, AA plus, we will refund you 90% of the cost of the Masterclass. So that is pretty much the best deal in town. If you find a cheaper tutor, you should hire him or her, because that's a nice guarantee right there. Anyway, that's it for the shameless plugs and the administrivia. I will be doing, again, one live stream a week, except this week where I'm going to do 2. And the goal is, again, just to be caught up. And you can try to watch these live if you want. I live stream on Wednesdays and Fridays when it comes to Physics 2. And if you catch it, great. But if you don't, obviously you can watch the recording either on YouTube or on our website, slacademia.com. Okay, let's dive into electric fields. So, Physics 2 is, at least this version of Physics 2, starts with electric fields. Now, there's a few issues with Physics 2. Might as well just talk about them right now. A lot of students don't like Physics 2, and the reason is in Physics 1, or Physics 8A, if you're familiar, it's mostly mechanics. You know, there's some fluids and some thermo and stuff like that, but the mechanics part is easy to visualize. If you have a cylinder rolling without slipping down an incline, you can pretty much picture it. You've already seen a cylinder, you can imagine something cylindrical, and an incline you've likely seen also. So it's very relatable. This class, Physics 2, is not relatable whatsoever. The overwhelming majority of what we will talk about, you have never seen or experienced in everyday life, and you never will. So, have you ever seen an electric field? No. I'm not saying there isn't a way to visualize electric field lines. I'm just saying you've never seen an electric field. You don't realize that you interact with electric fields. You have no intuition about them. Same thing for magnetic fields or induction or, EM waves in general for that matter. Not to mention interference and diffraction and quantum physics. Now, interference and diffraction, though, that might be the most relatable one. There are actually examples in everyday life, that you can relate to. But the point is, overwhelmingly, this is a class that is very abstract compared to the first half of physics. And the sooner you can get over it, the better off. So just don't try to visualize stuff. It's nearly impossible. You can't relate it to everyday life. And just learn the properties, learn how we decide to draw electric fields and magnetic fields, learn the formulas, and then kind of treat it like something abstract. It's almost like law in a way, where the law is the law. Yes, it's subject to interpretation, but it's just there. It came from somewhere, and you kind of have to just memorize it and know it, and then you can go from there. Well, Physics 2, in a sense, a little bit like that. It's like, okay, well, you have to learn the properties of electric fields. You have no idea or intuition about them off the bat, and you have to learn these properties and what you're allowed to write and not write, and draw and not draw, and then you go from there. Now, of course, the best thing is to do a lot of practice, as you already know, if you're taking Physics 2, because you've taken Physics 1 before. You cannot read about push-ups, you have to do them. Physics is the same thing. You cannot just read about physics, you have to go sit down with preferably a pencil and a piece of paper, my personal opinion, and go through problems. And if all you do even is set up problems and you don't solve them, that's actually already valuable. Of course, you actually also want to be good at solving them in a timely fashion for exams. So I would do both. But the point is, you have to put in the work and you have to practice. And you have to practice actively in the sense that you have to make sure while you're practicing that you're understanding what you're doing. If you're trying to do rote memorization, pre-meds, I'm looking at you, you will suffer unnecessarily is the only way to put it. I don't know how to say it otherwise. Rote memorization does not work for solving physics problems. Now, you should memorize all your lecture notes, all the formulas, all the examples that make sense, absolutely, because it's your toolkit, it's your baseline. But don't rely on rote memorization for solving problems. It is going to blow up in your face. And you can trust me because I've done this longer than you've been alive, or you can just find out for yourself, but it's not as effective. So anyway, let's talk about electric fields. Now, electric fields basically are going to be the main focus of this course easily for the first 3-4 weeks. We're going to have to talk about what they are, where they come from, what their properties are. That's mostly today. The force between two charged particles will come into play. That's also today, but I want to approach it from the angle of electric fields rather than look at it as just a new force. And then we have Gauss's law. Gauss's law is going to be a very clever way to compute the electric field created by some distribution, if there's enough symmetry, but it's a way to get the electric field. And then electric potential is a way to get a voltage or a potential difference between 2 points and look at electric fields, but from the point of view of energy. And so it kind of all builds on itself, and it's a big cluster of things. And well, we have to start somewhere, and we're going to start with electric fields. So let's start with a quick little overview of point charges and their electric fields E. Okay, so the electric field is denoted by E, capital E, and a point charge is, what's the equivalent of the point mass? If you remember in mechanics, we started by saying everything's a point mass, shape, size doesn't matter, just a point with a mass. Well, here it's the same thing, it's just a point, it's a mathematical point, it has no top, no bottom, no front, no back, it has no size. Mathematical point with a certain amount of charge. Okay, so we'll usually draw some kind of dot like this. Perhaps we attribute it a positive charge, plus Q, or perhaps a negative charge, it depends. You could have one or the other. That's one of the tricky things, is that mass was always positive in mechanics, but charge can be positive or negative in physics too. And we need to represent the electric field that surrounds these point charges. Now, we're going to, of course, we're going to define what an electric field is. We're going to write the formula for the electric field and all of that. But electric fields come from charges in general, but we're going to start with point charges. And you can think of the point charge, at least the positive point charge, if you want, kind of as a disco ball when it comes to electric fields. And so the electric field created by this positive charge is going to radiate outward like this. But if I draw it like this, I mean, I'm restricted by my little sheet of paper here, my screen. Obviously, it's two-dimensional. But the reality is that, just like a disco ball, this electric field radiates out in all directions of space from the point charge. So it starts at a positive point charge and points away. If I have a negative point charge, and let's just say that this charge is far enough from this one that they don't interact with each other. Like, typically they should attract each other, but they're far enough away that they don't know about the other guy. Well, in the case of a negative point charge, the electric field is going to be radially inward. Okay, so it's like kind of a reverse disco ball, kind of. That's weird, right? Like right there, that's weird. And of course, the fact that charge can be negative is going to be weird in some sense. At least it's going to take a little bit of getting used to, because we're going to see how it might mess us up in formulas later. Point is, electric fields are a property that surround charge. They tend to point away from positive charge and point toward negative charge. Now, maybe they start at plus Q and go all the way to infinity. Maybe they start at infinity and go all the way to minus 2Q. Or maybe if the two are close enough to each other, they tend to go from plus Q to minus 2Q, for instance. But in general, if you had to draw an electric field for these point charges, you would draw something like this. Now, it still doesn't really tell us what it is, but we'll get there in a second. Before we do, let's agree that right now it seems like the only difference is direction for my electric field, but really there is a difference in charge. This one's Q and this one's minus 2Q. Now we tend to adopt a convention, which is that the number of field lines is proportional to the charge. So if this charge in absolute value is twice as large as this one, well, I should have twice as many field lines, which means that really the right way to draw minus 2Q and its electric field lines is to draw something like this, where I have not 4, but 8 electric field lines that point toward the point charge. Okay? All right. Now, of course, the convention itself only makes sense if you have something to compare it to, right? If you did not have this guy here with 4 field lines for Q, then you have no reason to draw 8 field lines for minus 2Q. You just draw 4 if you wanted. So if you only have 1 point charge, you don't really worry about this convention. But it's good to know that it exists, and sometimes you have to use it, right? Sometimes you'll be given some charges and some field lines, and there purposely is a number of field lines that's proportional to the charge, which allows you to guess the charge, for example. So it's something that you should know exists, but more importantly, electric fields are a property that surround electric charge. They point away from positive charge, they point toward negative charge, okay? And so let's write that down so that we have a definition, and then we can worry about what happens when another charge interacts with an existing electric field, which is kind of the goal of today's chapter. Okay, so the electric field E is a property of the space surrounding charge. It represents the amount of electric force per charge at any given point. Okay, now that's weird. Electric force per charge. So obviously it's not a force, it's a force per charge, but really within the electric field you have the idea of force, right? It's just that your force is being measured per unit charge. So if you tell me how much charge I have, I can tell you how much force you're going to get if I know the electric field. So maybe a simpler way to say it is to say, well, if I take, let's say I take just this guy, yeah, and I make a copy here of this guy, all right. I have the electric field that points away. And at any given point, what we're saying is that the electric field will point to the right, if I consider this point. That will be the amount of force per unit charge. Okay. So if I place another charge, a different charge from plus Q, we tend to call these charges test charges because it is a charge with which we perform a test or an experiment. So we'll put a test charge at that location. And let's say that it's a positive test charge. Okay. Well, 2 positive charges are going to repel, and the result is that there's going to be a force acting on, now let me do this because otherwise we're not going to be able to see it. I'll extend this purposely, and there's going to be a force acting on this test charge that is going to repel it, right? This will be the electric force F sub E. Okay, well, I call it F sub E anyway. And I want the distinction because we'll have F sub B, the magnetic force, later. But F sub E is the force that plus Q exerts on the positive test charge. It repels it. And, well, if I know E and I know the amount of charge then I should be able to find the magnitude of Fe. Okay, so what we're trying to say is that the electric field represents the amount of force per charge at a point, and therefore a consequence is that any charge Q test placed at a location where the electric field is E will immediately experience the electric force Fe is equal to Q test times E. Makes sense. If E is force per unit charge, tell me how much charge I have. Q test multiplied by E should give me force. Okay? And so we're going to come back to that because we need to talk about this electric force thing. But the idea is that we've never seen electric fields in real life. We never will. It's kind of weird to understand what it represents. But you can either memorize that it represents force per charge at any given point, or you can say, well, if there is an electric field in the region surrounding plus Q, then if I place another charge in that region, it will immediately experience an electric force, Q test times the electric field at that point. So we need to be able, of course, to quantify the electric field at a given point, and we're going to get to that. But it might be easier to think of it that way. I don't know. Okay? But that is what the electric field is meant to represent. Of course, it makes sense because what it's trying to get at is that there's an interaction between these two charges. Positive charges will repel, opposites will attract, and so forth. But attract and repel means that there's a force involved, and that force is the electric force. Okay, so before we move on to the electric field created by a point charge and then the electric force acting on a point charge, because we do need to give some formulas, and those are the two important formulas for today, then we need to say one thing before we do that. So be very careful. Q cannot feel a force from E because it created E. Okay, so an electric field cannot act on the charge that created it, if you prefer to say it that way. Okay, you cannot say that the light beaming out of your disco ball is going to light up the disco ball. That's not true. It is leaving the disco ball, and it cannot be used to illuminate the disco ball. Kind of not a perfect example or analogy, but the point is, and you will see that this, you will trip on this at least once. The charge that creates the electric field cannot then feel that electric field. There has to be another charge, Q test, that shows up and says, oh, wow, an electric field. Now I can experience the electric force. Now, yes, Q test also creates an electric field, and then Q can say, oh, wow, look at the electric field created by Q test. I will feel an electric force because of that. But it can't be the case that Q is sitting all by itself at the bus stop and it's bored, and it's like, oh, look, I have created an electric field around me. Why don't I experience the electric force from it? You can't do that. You can't do it. The same way that you cannot exert a force on yourself, right? If you try to pull yourself, it doesn't work, right? Newton's third law takes care of it right away. It's like, okay, well, you're pulling that way, and then you also experience the force pulling the other way, and so you don't go anywhere. You can't drag yourself to the left or to the right. It doesn't work. Well, it's the same thing, okay? So if a charge Q creates an electric field, that electric field cannot then in turn act on the Q that created it. Okay, it has to be a different charge that is placed in the electric field. Okay, so something to keep in mind, and we'll come back to that in a second. All right, so let's look at the electric field E of a point charge, which in a sense we've already looked at, right? But here we're going to give the formula for the electric field. Now I'll use plus Q just as an example. But what I'm about to write will work even if it's minus Q instead. Right? And we already drew this, but I'm going to redraw it just to make a point. All right, so here I have 4 field lines. And it turns out it's a little too simple because my field lines are either horizontal or vertical. And mathematically, I have something that can describe horizontal or vertical. I have x hat or I hat, whichever one you prefer, for the horizontal direction, and then y hat or j hat for the vertical direction. So it is not difficult for me to describe the direction of this electric field, but that's only because I drew 4 field lines and not more. What happens if I draw more? Because I can draw as many as I want, right? If I only have 1 point charge, there's nothing to compare it against, so I can decide to draw as many electric field lines as I want. So maybe I like electric field lines and I find it nice to draw them. I draw 8. Okay, so now I have this guy here. Now that's neither along X or along Y. You might say, it's not too bad, it's 45 degrees. You're like, hey, it's in the middle, we can make it work. You're like, sure. But the point is, again, you can draw as many field lines as you want. You want to draw more, draw more. And at some point, the only common denominator is that these electric field lines point radially outward. That's what they all do. If you were to describe it with one single sentence, you would say that these electric field lines are directed radially outward. Of course, if the charge were negative, they would be directed radially inward, but the point is, it's one or the other, right? It's not to the left or to the right or something, it's radially outward or radially inward. And we do not have a way, mathematically yet anyway, to say radially outward or radially inward. Again, if we just, refer to our xy coordinate system, we can go ahead and say, oh, well, we'll just call this x hat and y hat. And if you prefer I hat and j hat, it's the same thing, right? X hat is pretty clear. It means 1 unit to the right. Everybody agrees. Y hat is pretty clear. 1 unit up. Everybody agrees. So if I say that this field line points along y hat, we all agree and we understand what that means. But what about this guy? It's neither strictly along x hat or y hat. It's both. So it's going to have components, which means components, we can't get away from them. We are going to use them eventually. But if I could only get one formula that condensates everything, which is typically what we like in physics, well, then I would do this. I would write that the electric field E is equal to, I'm going to write a KQ over R squared, but we're going to talk about K in a second. So KQ over R squared, that is going to be the magnitude of the electric field. But for direction, I don't have a direction yet. Well, I'm going to introduce something called R hat. And we're going to have to talk about R hat because it's usually pretty confusing the first time you see it. Okay. Now, sometimes, instead of K, we'll use 1 over 4 pi epsilon naught. So Q over 4 pi epsilon naught R squared along R hat. Means the same thing. Okay. So let's kind of go through this and unpack what we just wrote. First things first, K is short for 1 over 4 pi epsilon naught, and it's pretty much 9, 10 to the 9 Newton meter squared per Coulomb squared. And this is called Coulomb's constant. Oh, come on. A. There we go. All right. So K is Coulomb's constant. You can use K or 1 over 4 pi epsilon naught. We're not really in agreement. Some people prefer one over the other. I don't really care, but you should know that K is 1 over 4 pi epsilon naught.
and our hat means radially outward. That's what it stands for.
So it's 1 unit radially outward. Okay. Same way as x hat is 1 unit to the right. The difference is, to the right is always to the right. Radially outward, well, yes is always radially outward, but how do you draw it? Well, that depends where you are. Okay, so if we go back here, if we're at this location here, then our hat looks like this. But if I choose this location here, then our hat looks like this. Now both are radially outward, so it gets the job done. In fact, both are along the electric field. That's really nice. That's what we wanted. But you cannot say that wherever you are, our hat always points in the same direction if you mean left, right, up, or down. That's not true, right? X hat will always point to the right. That never changes. Our hat, well, will point in whatever direction it has to point so that it's radially outward. Okay, so we need to talk about our hat because, again, our hat is a very useful quantity to get one single formula like this one that is a compact formula that works for both positive charges or negative charges, because if the charge is negative, minus our hat will just mean radially inward, so it's going to work. But our hat very quickly ceases to be useful if I have more than one point charge. Because then if I have two, well, each point charge has its own R hat. You're like, oof, that's going to get messy. So we will, in fact, tend to revert back to the XY components when we have more than one point charge. But at least, hopefully this makes sense as to why we have our hat in the first place, why it's needed, and what it means. Okay, so point charges create electric fields. In fact, charge in general, but for today, point charges. And if they're positive, electric fields radiate away. If they're negative, electric fields radiate in. The magnitude at any given distance r from the center is going to be given by kq over r squared, or this. And of course, if you truly want the magnitude, you should probably take the absolute value of q. But the idea is that if you know q, if you know the distance r from the center, so this is the distance from the center to the point where you are computing E. Okay, and we'll do an example to illustrate this, but this is all you need to know to compute the electric field created by a point charge. Now, true, not everything in life is a point charge, and we'll deal with different objects that might have symmetry, might not, in a bit. We'll do some of it today, some of it on Friday. But for now, we have to start somewhere, and the most basic building block is the point charge. Okay. So, let's then talk about the electric force on a point charge. Right. Now the electric force on a point charge, going to go back to something we already talked about, and that's going to be Q test times the electric field. That's what we said. Okay, so let's say that we have an electric field. Okay, something has to create it. Now maybe it's another point charge, it's possible. Maybe I bought a machine that creates an electric field. Now, I don't need to know what kind of machine that is, or I don't need to know how I might be able to create a nice electric field like that that is uniform, meaning the same everywhere. It's nice and parallel, same magnitude everywhere. Maybe there's a way to do that. I don't know how, but let's just assume that we have that. The electric field is there. And then we take our little toolkit and we take test charges out and we place them in the electric field. Now, they are then placed in an electric field that they did not create. And so then they can say, ooh, an electric field. I will experience the electric force. And so if we put a positive test charge plus Q
we will find that the electric force acting on plus Q is going to be directed along the electric field. So the positive charge is going to get pulled along the electric field by the electric force. Okay, I'm going to redraw this so that, because if I draw another charge here, you're going to say, well, don't they interact, the two of them, with each other? It's like, probably, but I don't want that to happen. So let's look at a separate example where we now take a test charge that's minus Q. Okay, well, minus Q, again, it's going to behave in the opposite fashion, and it's going to be pulled by the electric force, but against the electric field. So the direction of the force depends on the sign of the charge, and of course the direction of the electric field that creates the force in the first place. But once again, we would prefer one single formula that's nice and all condensed so that it works in both cases, and that's going to be F sub E is equal to Q times the electric field. Okay, and so it works for both because, well, if Q is positive and I put a positive constant of proportionality between two vectors, the two vectors point in the same direction. But mathematically, if my constant of proportionality is negative, my vectors point in opposite directions. That's what I want. Okay. Now, I'm doing all of this, and I'm getting to this for a very specific reason. And I know I spent a little bit of time getting here, but a lot of textbooks and a lot of resources you'll find on physics, or even perhaps your professor will teach you that the electric field is force per unit charge, which by definition it is. And so we tend to favor, if we do that, the formula E is Fe over Q, which is obviously the same formula. There's nothing wrong with that. It's actually true. That is what the electric field is. It's a force per unit charge, so you have every reason to want to write it like that. I prefer to write it Fe is equal to QE, same formula, but mentally what it's trying to tell you here is that if you can figure out what E is, then you can know the electric force acting on this charge Q, right? And it turns out that the whole goal of today and the next live stream is to figure out how we can find the electric field created by one charge, multiple point charges, perhaps an object that's not a point charge. But if we can find the electric field, then we can figure out the electric force acting on a test charge that I place in it. Okay, so yes, on paper, E is Fe over Q. That is the definition. But in the practical reality, the way that we approach physics and we teach you physics and we solve problems, we typically want to find the electric field first to then get the electric force. And I'm going to try to illustrate this with Coulomb's law so that we're not confused about that. So let's talk about the electric force between 2 point charges. This is known as Coulomb's law. Now, I could have just called it Coulomb's law, but I want to emphasize that it is only true between 2 point charges. Okay? So don't start doing goofy stuff with Coulomb's law, trying to apply it between a point charge and later on an infinite sheet of charge, for instance. It's like, that's not going to work. It's only true between 2 point charges. Okay? If you have an infinite sheet of charge and a point charge, well, you're going to have to find the electric field created by the sheet first, and then you can find the force on the point charge. So that's a problem for later. But Coulomb's law is one of the first laws that we learn, and it has to be emphasized that it is only valid between 2 point charges. So let's think about this the following way. Let's define a distance r between 2 points. And at each extremity of the dotted line, I'm going to put a point charge. And I'll put a positive one and a negative one just to illustrate. right? Now we expect them to attract each other. Now let's start by putting only the positive charge, right? That's going to be Q. All right, let's call it Q1 actually. It's a good idea. That's it. No other charge. Okay. Now this is a positive point charge. A property of the space surrounding a point charge is to have an electric field, and this point charge is going to create an electric field in all directions of space surrounding it radially outward because it's positive. Okay, so Q1 is there, and along with Q1 you get the electric field E1. So in particular, if you wanted to look at this point right here, you would say that you have E1, and E1 is going to be in magnitude K Q1 over R squared. And now you could go ahead and say, well, this, I'll call this R hat. Well, and that's fine for Q1, but if you then put minus Q2, then R hat gets probably confusing. So let's do the following. Let's just call it X hat, because it is to the right, yeah? Okay. So that's the electric field created by Q1. And of course there's electric field E1 everywhere else, but the rule is we only draw the field lines we care about, and so I only care about this guy here because I'm going to put a point charge here. All right. So let me put minus Q2 here. Now, Q2 did not create E1, but if I place minus Q2 at this point where there's an electric field E1, minus Q2 will immediately experience the electric force, which in magnitude is Q2E1. However, Q2 is negative, so the electric force points in the direction opposite the electric field E1. This is going to be force of 1 on 2, and it's going to be minus Q2 times E1, which is going to be, and more room than that, which is going to be minus K Q1 Q2 divided by R squared X hat. Okay? Now this is consistent with opposites attract. Fair enough. And so I found the force acting on Q2. And what I did is I first placed Q1, I said Q1 creates E1, and then because E1 is not created by Q2, when I place Q2 in there, Q2 experiences the electric force, points opposite E1 because, well, Q2 is negative. Okay. But I have no reason to prefer Q1 over Q2 now. I could have made the same argument, I could have told the same story, starting with minus Q2, right? Maybe I do it again. I say, okay, well now I'm just going to start with minus Q2, right? There's no Q1 yet. Now, minus Q2 is a negative point charge. Everywhere in the space surrounding it, there is going to be an electric field that is radially inward that points toward minus Q2. In particular, at this location right here, where I'm eventually going to place Q1, I'm going to get E2, and E2 in magnitude is going to be K Q2 divided by R squared X hat. Okay? Now Q2 itself is a positive number because the minus here is what makes the whole thing negative. Okay, now if you prefer, you could write absolute value of minus Q2. Same difference. All right. And so now I just have Q2 and the electric field that it creates. I should call this E2. There you go. Now I take Q1 and I place it in at this location here within the electric field E2. Now Q1 did not create E2. Therefore, Q1 will immediately experience the electric force Q1 times E2. And because Q1 is positive, it will point in the same direction as the electric field. So this will be force of 2 on 1, that is going to be Q1 times E2, which is going to be K Q1 Q2 over R squared X hat.
Also consistent with the fact that opposites attract. Okay? Now, my point is the following. This is why I said Coulomb's law is only valid between 2-point charges. Because the magnitude of the force in both cases is going to be the same. Makes sense, that's Newton's third law. Whatever 1 does to 2, 2 does to 1 in an opposite direction with the same magnitude. Okay? So yes, the magnitudes are going to be the same. But the only reason that the magnitudes look like KQ1, Q2 over R squared is because E1 and E2 look like KQ over R squared. And that is only true if you have a point charge. Okay, that's a bit of an exaggeration because anything spherical turns out will end up getting the job done. But for now, E looks like that because we have a point charge. If I take a very long fishing line of charge, it's not going to create an electric field KQ1 over R squared. If I take a semicircle or a ring of charge, the electric field is not going to look like that. Same thing for an infinite sheet. Okay, so there are a lot of things that can create electric fields, but most of them do not create an electric field that is KQ over R squared. And so because E looks like this, the force looks like this. But again, this is contingent upon having point charges. And so we are going to write that the force of 1 on 2 is equal to the force of 2 on 1 and is K Q1 Q2 divided by R squared. But again, only true if you're dealing with point charges. Okay, so with all of that said, let's just quickly recap what we learned. We went over electric fields. Electric fields are a property of the space surrounding charge. Radially outward in the case of a positive point charge, radially inward in the case of a negative point charge. The formula that gives the magnitude of the electric field is KQ over R squared, as long as we have a point charge. And then this is a more general formula that the force on a point charge is Q times E. Now, E could be anything. Right now, we only know KQ over R squared, but it could be any other expression for the electric field if the electric field happens to be created by some other device or some other object that has charge. Okay? But if we only have point charges, and then if, therefore, E is KQ over R squared, then we get Coulomb's law between 2-point charges. They will attract if they're oppositely charged, repel if they're identically charged, and the magnitude of the force between them is KQ1, Q2 over R squared. Okay. So, let's do a few problems. Let's start with this one. This one's a classic, and it's going to be a good review of a whole bunch of vectors and geometry and things like that. And we'll see that it's going to be pretty useful to review that stuff because it's just going to be everywhere. So let's have a look at what we have. We have 3-point charges. Q1 and Q2 are positive. Q3 is negative. And a positive test charge Q, when placed at point P here, now point P is just a location, when placed at point P, will experience a 0 net electric force. Okay, fine. What if a negative discharge is placed at point P? What happens? Does it get attracted, repelled? Does it still feel a net 0 electric force? Who knows? Okay, so let's start with that. Let's start with just conceptually arguing that there is no difference because it's an important conclusion to come to. All right, so we have Q2, Q1, Q3. This is, we don't really need 3D and 4D right now. We'll get to that, but okay. And this is our point P. And we're told that if we have a point charge Q,
it experiences a net zero electric force. Okay, well, let's just draw the forces that it experiences from Q1, Q2, and Q3, right? Now, principle of superposition, which we haven't yet discussed, says that the net effect is the sum of the individual causes. So I can look at just Q and Q1 all by themselves, figure out the force, and not worry about the other ones. Then I can look at Q and Q2 all by themselves, find the force. Same thing with Q and Q3. I don't have to account for everything all at once. I can just superpose the results on top of each other, principle of superposition, to get the net force, which is nice. Okay, so Q is positive, Q1's positive. So, well, I don't know how big the force is. I could compute it, but certainly F1 is going to point to the left. Okay, Q2 is positive, and so Q2 is going to repel Q. F2 is going to point up. Okay, and again, I'm not trying to draw to scale or anything like that. I'm just drawing the forces. And then Q3 is going to attract Q because it's a negative charge, and so this is going to be F3. But I am told that the net electric force is zero. In other words, I am told that F net, which is F1 plus F2 plus F3, is zero. Now these are all vectors, careful, right? Okay, so however large each force is, whatever the direction of each force is, add it all together, they all balance out, and Q does not experience a net electric force. In other words, if I were to place Q at point P, Q just sits there. Doesn't get repelled, it doesn't get attracted, just sits there. Okay. Now what happens if instead I have minus Q? So let me make a copy of this thing here. Okay, and let's get rid of these. Oops. Let's do there we go. Let's get rid of these guys. What happens if instead I have not Q, but minus Q? Okay. Now the short answer is nothing changes in terms of the net force. But of course the individual forces are going to flip because now Q1 will attract minus Q. Q2 will attract minus Q, and Q3 will repel it. Okay. But of course, if you only change the negative sign, all you end up doing is changing direction. So, you know, if this is going to be F1, really, what you're really going to have here is minus F1, right? It's just in the other direction, but it's the same magnitude as before. Q1 and Q are the same in magnitude as before, same distance. Okay, so F1 here means minus F1 here. Same logic between Q, minus Q and Q2, right? This is going to be minus F2. And then between minus Q and Q3, you're going to get minus F3. Okay, so then what is the net force acting on this thing? Well, F net, by definition, F net is just the sum of these vectors. It's minus F1, minus F2, minus F3. Okay, but that's minus F1 plus F2 plus F3. And what we know about these guys is that they add up to 0. And so, okay, the net force is therefore still 0. So it doesn't matter, right? In fact, it's even better than that. You could double Q, you could triple it, you'd still get F net equals 0. You can make this minus 10Q if you want. F net's still going to be 0, right? Now the reality is because at point P, really what you have is a net electric field that's 0. So if you stand at that point and you're a point charge, you're like, well, there's no electric field, so there's no net force pulling me one direction or the other. All right, so that's the truth of the matter, is that really at point P you have no net electric field, and we'll see that in the second question. So it doesn't matter if you put minus q plus q, 15q minus a million q, you're still going to get 0 net force at point P. Now then, assuming q1 is plus q, what are q2 and q3? Okay, so let's redraw this a little bigger so we have some space to understand the drawing. And we're going to make this, and I'm not trying to make this to scale in any way, right? I'm just going to call this q1. We're told it's q. This is going to be 3D, yeah. Here we're going to get 4D. Okay, this is going to be q2. All right. And then here is going to be a negative charge. This is going to be q3. Okay. And our point of interest is here. Now let's just get some stuff out of the way right now. Let's just argue that this dotted line has a length of 5D. Hopefully everybody agrees. This is a 3, 4, 5 triangle, right? So the dotted line is 5D. If you're not convinced, Pythagorean theorem ought to get you 5D, right? Okay, so we know that distance. Then you could say, well, what do? We put a positive or a negative charge? That doesn't matter, so let's just put a positive charge, right? And then let's redraw our forces like we had them. We had F1 going to the left, F2 pointing up, and F3 going this way. Now, F1 and F2, pretty easy to account for. You know, pointing left, that's minus x hat, and pointing up is plus y hat, but then you're like, what about this guy? This guy's both along x and y. So the truth of the matter is that I'm going to need components for F3. I'm going to have to find the x component and the y component. All right. So this is going to be a good review. I mean, this is obviously a skill from Physics 1, but you need to be good at finding components of forces again. So call this theta, yeah? All right. Now if we go ahead and call this theta, remember that this is 4D. Let's just get this taken care of now so we don't have to come back to it later. Cosine theta is going to be adjacent over hypotenuse. So that's going to be 4/5. Sine of theta is going to be equal to opposite over hypotenuse, that's 3D over 5D. That's 3/5. Okay, so that takes care of that, because we're going to need that in a minute. Then, how do we deal with components? Well, let's do the following. Let's write the magnitude, just the magnitude of F1, F2, F3. Okay? Now, hopefully we all agree that F1 will have a magnitude K, Q, Q1, divided by the distance between Q and Q1, which is 4D. 4D squared will give me 16D squared. The magnitude of F2, with the same logic, is going to be K, Q, Q2, divided by the distance here between Q and Q2, which is 3D squared. So that's going to give me 9D squared. And then F3 is going to be, now this time I got to be careful, Q3 is negative, and my magnitude can't be negative, right? So this is going to be K, Q, absolute value of Q3, divided by this distance squared, so that's going to be 25D squared. Okay? But those are magnitudes. I can't just go add magnitudes. Yeah, that's not how this thing works. You have to use vectors, you have to account for direction, so you need to get your components figured out, right? So we need to figure out the component of F3 along x. That's going to be this guy here. That's the shadow of F3 along the x direction. And here we need to find the component of F3 along y. It's going to be this guy. That's the shadow of F3 along y. Okay. Now, hopefully we agree that f3x is going to be, in magnitude, it's going to be f3. Now, f3 is your hypotenuse. Your vector is always your hypotenuse. And then you have hypotenuse, angle, adjacent. So f3x is the adjacent component, meaning that f3x is f3 cosine theta. And then f3y, again, just in magnitude, is going to be, well, hypotenuse, angle, and then it's really the opposite side, right? So that's going to be f3 sine theta. But again, that's magnitude, yeah? So you could go two ways about it. You could say, well, shouldn't f3y be negative because like it points down? It's like, yes, you're right. But if I just want magnitude, I'm going to write like this. I do have to account for direction though, right? Now I typically do that when I write the net force. So we're going to write that what has to be true at point P is that f net x is 0 and f net y is 0. Okay. The net force along x is what? Well, F1 points to the left, so that's going to be negative. F2 points up, so that's not along x, so we don't worry about it. And shame on me, I know better. You should always show your x and y coordinate system. Okay, so F1 points left, that's negative. F2 doesn't matter, it's along y. And F3x actually points to the right, so it's going to be plus F3 cosine theta. That's going to be 0. Now, in the y direction, F1 points to the left, so that's not along y. F2 points up, that's positive, but F3y points down, so minus F3 sine of theta. That's equal to 0. Yeah? Okay, remember, cosine theta, sine theta. We're going to need these guys, so I'll bring them down here just to reference them. Okay. Of course, we're going to need all of this, so maybe I should just, there we go, do that. Okay, so this is going to be minus F1. That's minus K Q Q1 divided by 16 d squared plus F3 is K Q absolute value of Q3 divided by 25 d squared cosine theta. I'm just going to leave it as cosine theta for now, and we'll plug in 4/5 in a second. Okay. F2 is K Q Q2 divided by 25 d squared minus F3, all of this, sine theta. That's going to be 0. Okay? Now, with that in mind, we'll notice that Q goes away. Right? You can get rid of it. It's a common factor. It's not 0, so you can get rid of it. And what you end up with is KQ1 over 16d squared. And then KQ3 over 25d squared. Now, yeah, sure, there's a cosine theta there, but that's just for the component. And so the point is, just to go back to what we said earlier, one second, that yes, we're writing that the net force is 0, but the reason the net force is 0 is because the net electric field is 0. And my argument here is to say that what I just wrote on the right is the same thing as writing minus E1 plus E3 cosine theta is equal to 0, which means net electric field along x is 0, and then E2 minus E3 sine of theta is equal to 0. All right, so yeah, we wrote f net x and f net y are 0 because that's what the problem told us, but we could have just as well written E net x and E net y are 0. Okay, Now, of course, it's not the only thing that simplifies, yeah? K is going to go away with the same logic. D squared. I fumbled the ball here. Hold on. F2. Hold on. F2, that's not 25. Sorry, that's 9. Yikes. There we go. That's much better. All right, so then D squared goes away. And of course, I don't want 25 to go away. That wouldn't make any sense. They don't have the same magnitude. And as my undergraduate physics teacher used to say, Madame Bouvet, if you're watching, you can make a mistake in physics. You just have to catch it. So anyway, it simplifies that way. Okay, D squared goes away here too. All right, and so we're left with something rather manageable, which is, recall, by the way, that Q1 is capital Q. And we're going to get minus capital Q over 16 plus absolute value of Q3 divided by 25. Cosine theta is 4/5 is equal to 0. And then here we're going to get Q2 divided by 9 minus absolute value of Q3 divided by 25. Sine theta is 3/5. All right, that's equal to 0. Okay, so the first one tells me what absolute value of Q3 is. Okay, don't forget Q3 is negative, so we're going to have to say that specifically at the end. But if I solve the first one, I get absolute value of Q3 is going to be, now it's going to be Q over 16. I'll add that to both sides. Then I will multiply by 5 times 25 is 125 over 4. So this is going to be 125 Q divided by 64. Yeah, 64. All right, so that's absolute value of Q3. Convenient because I need it to get Q2, right? So Q2 is going to be 3 times 9 over 125 times absolute value of Q3, which is 27 over 125 multiplied by 125 Q over 64. Now that's going to be 27Q over 64. And we can therefore conclude that Q2, which is positive, is 27Q over 64. Pretty straightforward. However, Q3, because we're supposed to solve for Q3, not absolute value of Q3, right? Q3 is a negative charge, so yes, in absolute value it is 125Q over 64, but really there's a minus in front. All right, so then this is going to be Q3, and this is going to be Q2. All right, great little problem, not meant to be that complicated at all. If anything that I did here is rusty, foreign, not something you're comfortable with, you must, for your own sake, go back to look at vectors, look at components, figure out how to derive components, review your geometry, your angles, your cosines, your sines, your trig. You're not going to get through the class without it. You're just not. So make sure that you go review that if any of this is not clear, okay? But you do need to be comfortable drawing these forces, setting up your coordinate system, finding components, using cosine, sine, all of that, Pythagorean theorem, and then writing equations that are vector equations, right? I mean, f net is 0 is a vector equation, but the reality is we write f net x equals 0 and f net y equals 0. And so you have to be comfortable writing those and getting at your equations in component form. That's for the first problem, okay? And so now from there, what we're going to do is we're going to talk about something that it usually shows up in discussion, maybe not in lecture. If lecture is done well, it will show up in lecture, and it starts to address the fact that everything we've talked about today is electric field. And we talked about point charges. But we said electric fields are a property that surrounds charge, not just point charges. And not everything in life is a point charge. You could have certain objects that carry a charge. That could be a semicircle, it could be a ring, a disc, it could be a sheet, it could be anything you want to imagine that's not a point charge. And, well, we don't have a formula for that because, we said, let's go back up here real quick, E is kq over r squared. That's only true for a point charge. So how would we deal with such an object? And doing that means that, we're going to start tiptoeing into different objects with a certain amount of charge. And it's really going to be, part of Gauss, the goal of Gauss's law is this, right? Is to figure out E for objects that have a charge, but they have to have a lot of symmetry. If your object does not have a lot of symmetry and Gauss's law doesn't work, then you do what's called the slice and dice method. Okay. Now, slice and dice will get the job done every time. It's just a lot more painful to do it if you can instead apply Gauss's law because you have a lot of symmetry. But if you cannot apply Gauss's law, then slice and dice will get the job done. Now, what is slice and dice? Well, let's consider this semicircle of radius r that carries a charge q that is distributed uniformly along its length. Okay, so we've taken this semicircle and we've peppered charge around it, this total amount q, but in a uniform way. There isn't a piece that has a bigger clump of charge than another, just nicely spread out. And we want to find the electric field in magnitude and direction at the center of the semicircle of charge. Okay, so let's do a little bit of prep work here because we're going to need to look at two figures to really understand what's going on. So I'm going to draw a semicircle of charge here. And I'm going to make a copy here. Okay, and we'll see why. All right, so here and here is the center. Okay. Now what we're going to do is we're going to consider a tiny piece of the semicircle, and we're going to consider a piece so small, in fact, that we can treat it like a point charge. And if we can do that, well, then that's nice because we then have a formula for the electric field that that little piece is going to create. Yeah? So let me just finish this real quick. This is our coordinate system, really. And this is the center here. All right. Now, if I take a little slice right here, well, there's a few things I need to do. I'm going to redraw the same slice here. I need to know how small is small, and I also need to know how much charge it has. Okay? Now, in such a problem, and this is very common, if you distribute charge over a length, or over a surface, or throughout a volume, you get what's called a charge density, right? If it's over a length, we call it a linear charge density. If it's over a surface, it's a surface charge density, and then a volume charge density. Okay, but in this case, we have a linear charge density. Okay, and what it does is it describes how a charge is distributed. It's typically called lambda if it's linear. And it's going to be Q divided by the length here of my semicircle, which is half the circumference and is therefore pi r. Okay, and that is Coulomb per meter. So it tells me how many coulombs I have per meter on this semicircle. So if I know the length of my little piece here, then I can figure out how much charge it has. Well, this length here is going to be the smallest arc length that you can imagine that's non-zero. In short, that is going to be called ds. Thank you, Newton, for the notation. Right? ds means the smallest s arc length that you can imagine that is non-zero, which means that it is associated with the smallest angle here, d theta, that you can imagine that is non-zero. And if the radius here is r, then we get ds, nope, let's do that again. ds, by definition of the arc length, is r d theta. Okay, theta has to be in radians, but that is your arc length, right? So that's how much length I have. Well, if that's how much length I have, then the amount of charge I have, dq, is lambda times the arc length, ds. Okay, lambda is charge per length, okay, multiplied by length, ds. Yes, it's small, but it's still a length. I get dq is lambda ds. And this tiny slice, which of course, I mean, I drew it big enough to draw something, but again, this is the smallest slice that you can imagine that's non-zero, behaves like a point charge. Therefore, it's positively charged. At this point here, it's going to create an electric field dE in magnitude that is going to be equal to k dq divided by the distance here, which is r squared. All right, so that's the beauty. I have a slice so small that I can treat it like a point charge, and ta-dam, I now have a formula for E, or dE, that tells me the strength of the electric field created by that little slice that is equivalent to a point charge. Okay, now the problem is, how many such slices do I have all around my semicircle? Well, the answer is infinitely many, and therefore the price we have to pay for having sliced this up is that we are going to have to integrate all around our semicircle to account for every single little slice that you can imagine around the semicircle that creates an electric field at the center. But before we do that, and this is the part that is often forgotten, we have to argue symmetry. Okay, students get really happy, they find this and they're like, oh, I just need to integrate, right? And you can simplify this further. Yeah, I mean, dE, it's k dq over r. Okay, well, dq is ds, so this is going to be dq is lambda ds, so k lambda ds over r squared, and then you're going to say that this is k lambda r d theta divided by r squared. Okay, and that simplifies. You're like, oh, all I have to do is integrate d theta, and by the way, I can figure out what theta is, right? Now, theta is going to denote the location of your slice. So this could be theta, or this could be theta. That's up to you. You pick one or the other. I'm going to pick this case. But if I pick this, then theta equals 0 is going to be here. And to go from one end to the semicircle to the other, I'm going to have theta is minus pi over 2 here, and theta is pi over 2 here. Okay? So, and this looks weird the first time, but the good news is the semicircle, you always deal with it the same way. Okay, the ring of charge, same way, disk of charge, same way. So there's only so many of these slice and dice problems that you can do manually, right, without having to use a computer to calculate the integral. And they all work the same way, so you should memorize them and know how to do them. And this is one of them, it's a semicircle. Okay, so before we integrate, right, we need to do the following. We need to say that, okay, dE has two components. It has dEx and dEy. And what I could do is the following. I could integrate dEx to get E sub x, and then I could integrate dEy to get E sub y. And if I had both components, I'd be super happy. I would know exactly the electric field at the center. And I could do that, it's fine. It turns out that this is going to be 0. And I can do it and calculate a big integral and get 0, or I can argue ahead of time that I know that it's going to be 0 from the symmetry of this shape. Okay. So what we'll do is the following. We will take, on the other side here, of the semicircle, we will take an equivalent slice with charge dq is lambda ds. And this equivalent slice will create an electric field with the exact same magnitude right here. Okay? And for any slice here on the left, I can find a corresponding slice on the right. And what I'm going to find is that the x component here of dE is going to cancel with the x component here of dE. By symmetry, they're the same. So net, there's going to be no x component. The only components that are going to matter are the y components, because the y component of dE points down, the y component of this guy also points down. So all the components pointing down add up, and the only one I care about, therefore, is dEy. Okay? And what I can say is that dEy is dE cosine theta, and that is going to be k lambda cosine theta over r d theta. Okay, and if you forget that piece, which is the piece that is most often forgotten, ask me how I know, then you forget cosine theta. And it's very different to integrate just d theta versus cosine theta d theta. Okay, and so we're going to say by symmetry, Ex, which would be the integral over the semicircle of dEx, is 0, and the only component we care about is Ey. Now, Ey will point downward. We'll get to that. Okay, and if we say that this is, if y is positive up and x is positive to the right, it'll be along minus y hat. But what we want to do is we want to integrate over the semicircle dEy. Okay. Now that's going to be the integral of this thing here. Okay, now at this point I have to really quickly check that my integral is in terms of one parameter or one variable, because I only know how to integrate over one variable. Okay, now theta d theta, that's good. D theta means I integrate with respect to theta. Cosine theta is in terms of theta. Obviously theta changes as I go around the semicircle. And then everything else is a constant, so it's not a function of theta or something else, right? Whatever happens here, I have to make sure that I've parameterized my integral to be only in terms of one variable, right? And so then we'll go from, I say this, if you go look at the finite rod of charge and you'll find the electric field above the center, you will see that there's a little bit more work to do to get your integral cleaned up. But here we're going to integrate from theta is minus pi over 2 to theta is pi over 2. And while here, if you don't remember your calculus, I recommend you go refresh your memory on antiderivatives and all of it. So k lambda over r, the antiderivative is going to be sine theta, to be evaluated between pi over 2 and minus pi over 2. Okay, so this is going to be k lambda over r sine of pi over 2, which is 1, minus sine of minus pi over 2, which is minus 1. And so we're going to get 1 minus minus 1, which is 2, and we get 2 k lambda over r. And so we conclude that Ey, or just E actually at the center, sorry, is going to be minus this y component, 2k lambda over r, divided by, or times y hat. Duh. Okay, that's the electric field at the center. Now, a few things. First of all, this is magnitude and direction, so that's good, you need both. Second, it depends on the problem what your answer looks like. So recall that here we actually said lambda is q over pi r. Okay? So really, our answer should be E is equal to minus 2kq divided by pi r squared y hat. That's the right way to present the answer. But that's because the problem provided me with q and r. Didn't have to. Let's go back to the problem. I could have said, hey, here is a semicircle with linear charge density lambda, and I don't give you q and r. Well, you probably need r anyway just to do the work, but I don't give you q, let's say. I just give you lambda. Well, then your answer should be in terms of lambda. So students sometimes get confused because they don't understand why. In some cases it's lambda, in some cases it's q. How do you know? Well, it just depends what you're given. Okay, I needed lambda to do the derivation, but since I know q and r, at the very end I should sub that back in for lambda. But if the problem just goes ahead and says, here's a semicircle of charge with uniform linear charge density lambda, then you can just use lambda, and your final answer is going to look like this. So that's what we call the slice and dice method. Okay? And the slice and dice method is a way to take an object that is not a point charge and cut it up into a piece so small that you can treat it like a point charge, but the price you then have to pay is that you have to integrate over the object, over the charge distribution, to get your electric field. Okay? Now again, this works for anything. The price to pay is a complicated integral potentially. So if you're talking about doing it by hand, typically you have the finite rod of charge, the semicircle of charge, which is what we just did, the ring of charge, and the disk of charge. Those are the four that you should know how to do, and once you know how to do them, the good news is the derivation is always the same, right? So it's one of those questions where if you've never seen it before, it's a very hard question on a test. It's almost unfair if you've actually never heard about slice and dice. But if you have seen it before, it's a very simple question. And it turns out that most of the time, if the problem is interesting, maybe it starts with you finding this electric field here at the center, created by the semicircle. But there's three more questions that are really the interesting questions. We're just saying, okay, find E, because we know you know how to do that, so it'll get you going on the problem, build up some confidence. But really, we want you to find E only because we want to ask you about 2, 3, and 4, right? So it's something that you should know how to do. I would definitely encourage you to memorize and to know how to derive these 4 cases that I mentioned. And then you'll see when it shows up in a problem, well, half the problem is not that intimidating anymore because you at least know how to tackle that bit. So anyway, that's going to be the end of the public part of this physics review. Again, we went over electric fields. Next live stream, we're going to go over Gauss's law, which is how to find the electric field in case of a charge distribution with a lot of symmetry. We kind of already touched on how to find the electric field for something that's not a point charge, right? So we want to get good at finding electric fields for charge distributions. Gauss's law is going to be a tool in that toolkit, and then from there we're going to go to voltage and electric potential, because once we know the electric field, we can talk about voltage and electric potential. So that's kind of how the first 3 weeks of class are going to articulate each other, or with each other. And today was kind of just, we had to get started with something, and point charges and electric fields mostly, and at the end, this idea of slice and dice. So again, if you want to find these live streams, the problems, and solved homework problems, you can go to psychedemia.com/live streams, enroll in the free Physics AP live streams. If you want a study guide or a study guide plus my help, you can go sign up for a study guide if you find one that already exists for your course, or we can create one for your specific course with your specific syllabus. Just contact us and we're happy to do that. And of course, with the Masterclass, you get access to me all semester or all, your whole quarter, whatever the case may be. And if you don't get some kind of A, you get a 90% refund, so that's pretty much a no-brainer. With all that said, thanks for watching as always. If you don't watch, this doesn't work, and I will see you on Friday